Our next speaker is Tomas Vondra. He's a major Postgres contributor, committer. He works at Microsoft, and he's going to tell about fast path locking. Please give him a round of applause.
Okay, so hello, welcome to my talk. I'm Tomas Vondra. I work with Microsoft, and I'm here to talk about fast path locking and especially fast path locking improvements in PostgreSQL 18. When I first gave this talk a couple of months ago at a different conference, I didn't realize it's actually only a 25-minute slot, so I had to rush a little bit, but I made it shorter, so now I have, instead of 30 slides, I do have 40, right? So I will have to rush a little bit more, but hopefully it will be comprehensible. So what's the agenda of this talk? What I would like to go through here. I will be talking about one improvement in PostgreSQL 18, but when I was preparing this slides, I want to do it a little bit differently. Instead of just talking about the end result, I wanted to also explain a little bit how we ended up there, like why we did the improvement, and also explain a little bit about the dead ends, right? Like things that didn't work. And so I will be talking a bit about history. I'll be talking about what he ended up doing in Postgres 18, and what are the trade-offs that we had to do, and also like challenges and things that we still need to improve in future versions of Postgres. So why was I looking at this at all, right? Locking definitely is not a new thing in databases. Like every database has to do some sort of locking. But we did get a report from a customer doing fairly large systems, like processing many queries. And they've been also using a partition table with like not insane number of partitions, but maybe a couple dozen, like 20 or something like that. And the customer upgraded to a new CPU, like a new system, which had significantly more cores, significantly more CPUs, a little bit slower, but they did expect, thanks to the concurrency, they did expect like significantly better throughput, right? And they saw exactly the opposite thing, right? You did get like twice the number of cores, and you get half the throughput. Like, something is not right. Something doesn't work as expected. So this is why we started exploring like this topic, right? And just to give you like an example that it's not like a crazy thing, this is how you would do that on your machine, right? You initialize a PG bench, which is with a very, very small scale, so that everything is in memory essentially, with 10 partitions. And then you do a little bit like a small DDL change, which adds a new column, which is exactly the same thing as the account ID. It just is not the partition key. And we do this, and then you do like a small join with filter on the new column. If you have a little bit experience with partitioning, you will understand that this has one unfortunate effect. You will not be able to eliminate partitions based on the value, right? So this join doesn't allow you to eliminate partitions on PG batch accounts, right? You still have to select from all partitions, like scan everything, even though the partitions are tiny. The partitions, this is only like 100,000 rows, maybe 15 megabytes or something like that. So to do this query, you still need to select and plan the query with all the partitions. And the query plan will look something like this. I mean, like it's a fairly simple join with just 2 tables. But the important thing here is that we need to do index scan on each partition, right? Even if you logically know that the ID can be in only a single partition, database doesn't know that, it still needs to do all the planning. And this is a terrible throughput. This is a database system that can do millions of transactions per second, right, of simple queries. If it was able to eliminate the partitions, it could do like 10 times this. But this is with 10 partitions, and this is with 100 partitions. And you can see that this is with simple queries, and this is with prepared statements, which means like this is a difference between when you do the query planning, and this is when you don't need to do the query planning. So you can see that there is a significant impact of that. And of course, the number of partitions also matters, right? So if you go from 10 partitions to 100 partitions, the throughput goes down like 10 times, which, okay, I mean, like, you need to process like 10 times the number of partitions, but the amount of data is the same, right? You just have the data divided into more partitions. So this just doesn't sound right. And also, as I said, like, it's a system that can do millions of transactions per second without the partitioning. So why is this happening? And the other thing is, of course, that the system has 80 cores, but we stop scaling at like 30, right? So you keep adding like CPUs to the system, it doesn't actually help. So these are all signs that there is like a significant bottleneck somewhere, right? So why is this? Well, what we do as engineers, we jump to conclusions, right? Like you see a new problem, say, oh, definitely it has to be this, right? So that's what we did, or what I did back then, because we do have we have a log table in shared memory. The log table is partitioned, right? So that when you are adding a log into the hash table, you only need to log a small portion of that. And we only have like 16 partitions by default. So we decided to just increase that to 64, right? So you have like 4 times the number of partitions, and it didn't help, right? So this intuition was completely wrong. We spent like a week on testing that, but it was wasted time. So it has to be something else. So it's probably time to do, a proper analysis, right? So what you do, well, no. You first start to invent crazy ideas, what could be causing that. First, it could be power management. We saw a similar issue at the same customer, like years ago, where like one of the CPU fans was not working properly, right? Which means the CPU was throttling down, and it was causing like slowdowns exactly like this. It wasn't this case this time, right? Then we could have like problems with like multi-threading and SMT and so on, because when you are running more threads, maybe the CPUs can't go to a higher frequency, right? So, and we have seen like strange effects with disabling hyperthreading actually helping and things like that. So it has to be about concurrency, about the number of threads, but it's not SMT like itself, right? And of course, there are like other bottlenecks, because what you see in systems nowadays is not that you are hitting one bottleneck only. You are probably hitting like bottlenecks in different parts of the system. So maybe it could be something like malloc contention, which is a problem on large systems, especially with the glibc. It can be pretty bad. And there is a little bit of that in this case, but it's not like the primary cause here. So, okay, time to actually do the proper thing and actually profile the thing, right? So this is a CPU profile on a process running the benchmark. And you can see that like 50% of the time is spent in log relation ID, which is exactly the thing that is actually inserting data, inserting the records into the shared log table, right? And the locking in Postgres works so that if you have even a short query, it inserts all the logs into the shared log table, and then at the end of the query, it removes them again, right? So it's quite a busy part of the code. If I show you the flame chart instead, and the pink parts are exactly the part of the code that is responsible for maintenance of the shared log table. Then you can see that it's like roughly like 50% of the CPU time is actually spent there, right? These are like operating system functions in the kernel responsible for maintaining some sort of like semaphores and view texes and so on. So clearly the problem is in maintenance of the shared log table itself, right? It's just expensive to do, modify the log table with significant concurrency. So what we can do with that? And I'm getting to how the fast path locking actually works. So a simple view on locking in Postgres of relations is illustrated by this image. You have a connection, which is like the backend process running the queries, and it's inserting data into the shared log table, which is internally split into two parts, logs and proc logs, but that doesn't really matter here. And it inserts data, inserts records, which are fairly large, like half a kilobyte each. And this is the log table that is partitioned, right? You have like 16 chunks here, and each log belongs to one of those partitions. But it's kind of expensive, right? Like maintaining this shared memory is expensive, and also the capacity is pretty significant, right? Like you do have a configuration parameter which is called max logs per transaction, and we size the shared log table based on that, right? So we can actually get at least this number of logs from each individual backend, right? But it's not a per backend limit. So if you look at the log, at the documentation describing the log levels in Postgres, you will see something like this, like without the red square, that's what I added. But you will see this table, which shows you which log modes conflict with each other, right? And the interesting thing here is that these low-level logs, like access share, row share, up to share update exclusive, well, up to row exclusive, they do not actually conflict with anything else. They don't conflict even with themselves, which means like if you are running a select, which is only selecting data, it doesn't need to block with other select, right? Those two backends effectively do not care about each other. And that's the idea behind fast path locking, because it means like if you only do this type of access to the data, you don't need to care about other backends that also access data this way, right? And the idea here is that, well, I don't need to actually insert the logging information into the main shared log table, which is in shared memory and is constantly accessed by other backends. I will only insert this data into like into small buffer in shared memory, but it's still in shared memory, but not accessed by other backends at all, right? So there is no conflicts on locking. The other backends do not wait actually on this, right? But what happens if there's like a DDL, like something that actually needs to acquire a log that would conflict, right? If you have something like access exclusive, it will need to worry about this kind of logs. So that session will actually inspect not only the main log table, but will also go through the other parts of the shared memory and will do the expensive thing of actually collecting all the information from other backends. And that's fine, because the DDL is going to be expensive anyway, and it's only a very rare thing, right? You do not do alter table in every transaction, right? You do that maybe once a month when you are deploying new version. It's fine if it's more expensive, right? So that's the idea behind fast path locking. The fast path locking is not a new thing. It was introduced in Postgres 9.2, which is like ages ago, right? It's like 12 years ago, I think. And the idea is that we do have a fast path array in pgproc, which is the main structure in shared memory, keeping information about processes, about backends, for example, and it serves as local cache. And there is a fast path protocol, which is described in log.c, and it's described in a README next to that. The whole idea is that if you are only holding the permissive logs, you don't actually need to insert data into the expensive shared log table. And only if you are obtaining a conflicting log, like something like access exclusive or and so on, you do actually need to inspect this information. The main problem is that because it's part of the pgproc struct itself, it only has space for 16 OIDs, right? An OID is the thing that, that identifies a table, a partition, or anything else that qualifies as a relation in Postgres, which is, for example, even an index, right? So if you have 10 partitions, and each has an index on it, you already need like 20 OIDs. And you are over the 16, the capacity of 16 OIDs in that. What happens then? Well, the things that do not fit into the small buffer, you insert that into the expensive shared log table, right? And in versions since 9.2, the capacity is fixed, right? You only have capacity for 16, which works fine for like most queries. But once you, for example, introduce a declarative partitioning, which we did in, I think, Postgres 9.6 or 10, and people start actually using more partitions, even relatively small numbers of partitions, it's very easy to hit that. So what do we do? Well, first I will show you like the effects. This is from a different talk I gave last year at this conference. And it shows throughput with different client counts, like one client, 16 clients, up to 256, on a slightly different workload, but it's a join with different numbers of partitions. And these are versions of Postgres, right? And you can see that in like Postgres 9.2, there was a massive improvement since like 32 clients, it jumped like an order of magnitude up, thanks to introduction of fast path locking, right? This thing with the small buffer was introduced in 9.2. And then you can see some additional improvements, like in Postgres 14, we improved the scalability of a different part of the database, and that also helped a lot. But then we stagnated for a couple of versions, and now in 18, thanks to the improvements in fast path locking, there's a significant like improvement in throughput again. And this is the thing that I'm talking about today. Like one comment about this is that every time I claim that like we are doing the best we can, like there is no way to improve the throughput of the database again, Andres immediately comes and like does something like this and like fixes a bottleneck somewhere. So just don't do that. So we obviously need to improve the throughput, right? We need to increase the size of the fast path buffer. So how do we do that? That's the first question. Yeah. We can't really keep that in pgproc anymore, like in the struct itself, because that would require the the size of the buffer to be fixed, right? You can't have an easy way to variable length structs in C, because we need to keep like an array of those structs, and that wouldn't work. Also, how do you actually tune that? Like, if it's variable length, someone needs to pick the size. Usually, it's going to be like a user through some sort of configuration options in the configuration file. And it still needs to work with the original fast path blocking protocol, right? Because that's tested. We know that it works. We know that it actually does the correct thing. And there is like a link to the README for the details. So my ambition in this project was to make it flexible, make it like variable size, and make it larger. But how should actually it work? Like, what should be the data structure? This is how it works now, or well, how it worked before this improvement. We had a buffer of 16 OIDs, and OID is just like an integer 4 bytes each, right? So we have like 64 bytes, which nicely fits into a cache line, which is 64 bytes on most CPUs. And it's very simple. Whenever we are looking for or inserting a data into that, we do a linear search for a matching or empty slot, right? So, and that works perfectly fine because everything is in a cache line, it's fast. You can't really beat that with, say, binary search with this number of elements. So how do we make it larger? Well, first, we could just like make it much longer array, right? Like, instead of 16, I think this is like 64, like it's like 4 times the size. And we could keep doing the linear search, which did work perfectly fine with 16 elements, but it's going to be like terrible with like 64 or more than that. So we can't really do that. That would be completely defeating the purpose of like fast path blocking because it would make it slow, right? So the other option is to do a hash table, like increase the capacity of the array and do like hash table, hash the OID, and then that tells you which slot that is. If it's already used and you can't insert there, we have the luxury of just inserting the data into the shared log table as like a fallback. That's fine. But it's not great because it's very random access, right? And even in RAM, even in memory, the sequential throughput is much better than random, right? So this wouldn't work, right, either. So what do we do is actually we combine those two things, right? So you first do the hash, and that tells you which part of the array the value is going to be in. And then in the small 16-element array, you do the thing we did before, like the linear search, right? And that combines, like, it gives you better capacity, but it also gives you the benefit of hitting the cache lines, right? So you get into one cache line, and then you scan the 64 bytes, which the CPU can do really fast, right? And when I came up with this, I was so proud, right? Like, because this seems like super efficient struct. I was very happy with that. And I thought, like, oh, I invented something new. And I did not, because this is what CPUs are doing for the last 20 years, right? Like, this is what CPUs call set associative cache, which means that for a value, you have a bunch of locations, in this case, 16 possible places where the value can be. And yeah, that works very fine. So we do data struct like this. This is just a summary of the previous couple of slides. And it's a very simple concept. It has a nice sequential access pattern. It doesn't have problem with limited capacity because you can do it as large as possible. as needed. And this is the effect on the throughput, on the performance. So this is the original flame chart like before, right? Those are the pink parts that are really slow. And this is with the fix, right? Like the pink is almost gone. Like there will always be a little bit of that, but it also means that we went from 20,000 transactions to 200, right? So it's an order of magnitude improvement. There are other things that I needed to fix in the operating system and so on, to reduce the malloc overhead, but this is the effect of that. The effect on the throughput on the chart looks like this, right? So this is one with 64, with the capacity set to 64. If I improve that to 1,000 for 100 partitions, the improvements are even more significant, right? So the trade-offs are, there are multiple trade-offs. First, how do you configure that? We ended up tying that to an existing GUC. We do not want to introduce a new GUC for each new feature, because then we don't know how to tune that, and users don't know how to tune that, and that's terrible, right? So we tied that to max logs per transaction. So if you already set that to work, it should be a good starting point. There's no optimal value for all systems, but it's also very cheap, right? You are allocating a bit more memory, but it's probably better to use a larger value, not insane, but 1,000 would be perfectly fine, I think. The default, we didn't change the default of the GUC, so by default you get 4 times the capacity of before, right? Because it used to be 16, now it's 64. So what's next? We do need better monitoring for this, right? Because it's really difficult to now deduce what is the proper value of the GUC. You don't know how often you overflow the fast path buffer. PG logs is not a great source for this. It's just the current view of which logs you are holding now. It doesn't tell you exactly the statistics that you need for tuning. That would be a good patch, I think, for someone, right? It doesn't seem extremely difficult to add a view like this. Famous last words, I know. The other thing is maybe we could use a similar idea with the set associative caches elsewhere. Maybe we could consider hotness when evicting some of the logs into the shared log table. I don't know. There are definitely some NUMA effects affecting this, right? So maybe we should, partition the shared memory to consider NUMA nodes. And of course, we could make the shared log table cheaper. We should do that, if possible. But I don't have a good idea how to do that. There are definitely some other bottlenecks that you can run into. It's not just you will remove this bottleneck, make fast path locking cheaper, but you can run into glibc malloc thing. I just don't have time to discuss all of that here. We do have problems with join order planning in some cases, especially with star joins and so on. It's possible to actually get into a situation where that is actually the main bottleneck, right? And you can probably hit multiple bottlenecks at the same time. So I'd like to shout out to Robert Haas, who is he introduced the fast path locking in Postgres 9.2, and the code was amazingly easy to actually introduce this additional layer, right? So I was surprised because it compiled and it worked on the first try. And it was not because I'm smart, but because he made the code in a way that made this possible, right? So I do appreciate that. And I think also thank Jakub Varťák, who is somewhere here, I think, who was the support engineer helping me with actually investigating and discussing this problem. And I wouldn't be able to get this done without him. So that's all I had. I think I'm exactly on time. There's a feedback QR code. So the slides are already on the conference website. So feel free to download them. The other thing I would like to mention is that we do have a conference in Prague at the end of January. And we are currently looking for papers or talks and workshops proposals. It closes on November 14. We are also looking for sponsors, right? So if you are interested in supporting a small conference of 300 people, that would be nice. And we also have a Prague PostgreSQL meetup. Gulchin and Mayur are somewhere around here, and they are also looking for speakers, right? So that's every month there is a meetup. And that's all from me.
Thank you very much. We don't have time for questions. Please send him patches instead. Thank you.
Thank you.
And next up, we have a coffee break.